Good morning or good afternoon, everyone, depending on where you are joining us from, and welcome to today's webinar. My name is Simon Thorpe from the Business Review, and I will be the host for today. It's our pleasure to have Paqell with us today, who will be discussing gas desulphurization made safer, easier, and more efficient. Today's guest speaker is René Bakker. René is the Business Manager for Paqell. Just before we get started, I'd like to take this opportunity to remind the audience that you can submit questions using the Q&A tool at the right-hand side of your screen, and you can do this at any point throughout the presentation. We will then allocate around 10 to 15 minutes to try and answer any questions or thoughts that you might have. So, without further ado, please allow me to welcome René. Over to you.
Thank you, Simon, for the introduction. Ladies and gentlemen, welcome to the first Paqell webinar. My name is René Bakker, Paqell Business Manager. In the next 50 minutes or so, we will summarize the small to medium-sized gas desulphurization landscape, describe the challenges you face, and present THIOPAQ O&G as an alternative solution that may be of value to your organization. This slide should really display the content, but due to a slight error, it doesn't really work as intended. Anyway, in this webinar, we shall touch on the why and the treating options available in the market, zoom in on THIOPAQ O&G, and discuss operations, cost, and sulfur outlet options. Finally, I shall try to provide you with a feel for both OPEX and CAPEX. An orange indicator at each top left-hand side enables you to keep track of where we are. You can mail any questions at any time during or after the seminar, as Simon outlined just now. I will answer as many questions as time permits live at the end of the webinar. All remaining questions will be answered by us within the next few days. Paqell was established about 2 years ago as a 50-50 venture of Shell Global Solutions International and PAX, a Dutch water treatment company. Just a little bit of THIOPAQ history. A Mr. Sergei Vinogradsky discovered the sulfur oxidizing bacteria well over a century ago. And these days we call our little friends Thio, because it nicely alliterates with thio, the Latin word for sulfur. Actually, Thio narrowly escaped being called Sergei. In the 80s, the University of Wageningen in Holland researched various types of sulfur bacteria and established that sulfur oxidizing bacteria could indeed live, grow, and multiply off the oxidation of sulfur in a controlled environment. It was our shareholder PAX that first piloted THIOPAQ biological gas desulphurization in the late 80s, after the Dutch University had established proof of principle a few years before. PAX had been searching the market for more affordable and easier to operate systems to treat the biogas produced in their anaerobic wastewater treatment units, until they came across this biological treatment option, which they decided to develop into a commercial installation themselves. This picture shows the first crude bioreactor, still rectangular rather than the cylindrical design adopted immediately after. Next, this wintry picture. Shell bought into the technology in the mid-90s after testing on high-pressure natural gas in Germany had clearly demonstrated the full potential of the technology. Eventually, the first commercial unit on natural gas was taken in operation in 2002. And this picture of the unit clearly shows the insulation blanketing, since Canada can be pretty cold in winter. Between 2002 and today, the number of the THIOPAQ O&G units steadily increases to about 10, with many more in the design and quotation stages. The picture in the middle was taken to celebrate the partnership with Cameron in 2011. The same year, Paqell was established. Paqell is located in Amsterdam, the Netherlands, and the reason for its creation was to put more focus on marketing and further development of the THIOPAQ technology. Now, maybe an insult to your intelligence, but just for those of you who are new to gas treating, the question, why remove sulfur from gas in the first place? H2S is very harmful to people and equipment, and it also means that desulphurisation at some distance from a sour source is very expensive, as more exotic materials must be used and additional safety measures need to be taken. Most sour gas is of one of these types. Acid gas, of course, could originate from any gas fed into the amine unit in question. Although any of the types listed here can be treated with THIOPAQ O&G, for the purpose of this webinar, I would like to focus on the types within the orange frame, right here. Just wanted to run you past the common alternatives available on the market next, quickly starting with scavenging, which is a very good solution for smaller quantities of sulfur up to roughly 300 kilos per day. It's a chemical solution or granulate loaded with H2S until saturated, and then typically the spent chemicals are taken off-site for regeneration or disposal. It's very low in capex, but extremely high in opex. Think in the 10 to 15,000 US dollars bracket per ton of sulfur removed. Next in line, chelated iron from, for instance, blowcat or sulfur ox. They've been around for some time and can be a very effective solution. But typical drawbacks are associated with the cost of various proprietary chemicals, operational issues due to system plugging, and contamination of the sulfur produced, which complicates the search for a suitable sulfur outlet. Amine units do a very good job by separating off sour components of the feed gas, such as H2S and CO2. These components then need to be physically recovered by another technology lined up after the amine unit to process the concentrated off-gas stream. For larger loads, typically Klaus-based technology are applied, but alternatives such as THIOPAQ or any chelated iron system can be used as well. It's preferred for small and larger loads. Next, the familiar, at least to most listeners, familiar Klaus unit. Based on the Klaus reaction, it all starts with a burner fueled by the H2S, which will burn well if the concentration is over 30%. The end product of this complex system is pure liquid sulfur, bright yellow in appearance. An added bonus is the fact that waste heat from the burners can be used in boilers to produce medium pressure steam, which in turn is a very nice thing to have in refinery and petrochemical facilities. An amine Klaus lineup can be used to treat even smaller quantities of sour gas, at least in theory, especially when the concentration of H2S in the amine off gases feeding the Klaus unit falls below 30%. Very expensive measures need to be taken, effectively restricting the application to higher loads, able to bear the high capital expenditure by making the cost per ton of sulfur produced acceptable to the owner. The challenge. The slide states the reasons why traditional amine Klaus technology is often either impossible or very uneconomical for a particular project. In natural gas, we see an increase in production from smaller sour wells and wells low in sulfur content, such as, for instance, shale gas. For associated gas, or associated petroleum gas, there are fluctuations in flow as a result from fluctuations in oil production, and typically smaller sulfur loads and low sulfur content here as well. At the same time, regulations on sulfur emissions to air tighten, which rules out flaring in most places in the world today. This leaves you with the challenge we state here: how to remove sulfur from small to medium-sized sources with unfavorable gas compositions. Why is removal from these smaller sources really a challenge? It is because very often you lack the tools to overcome the issues stated here on this slide in a way that will satisfy requirements set by disciplines such as HSE, safety, finance and operations. At this time, we would like to launch the first poll of this session. You should see that on the right-hand side of your screen, and we would appreciate it if you took about 1 or 2 minutes to fill out. And we will publish the results later on in the presentation. Now, next question after describing the challenge is: how does THIOPAQ Oil and Gas meet the challenge? Rather, help you meet the challenge. This is one way. A process that is simple, safe and stable, and within the segment, economically attractive. It can replace the entire traditional lineup, which looks complicated even as a simplified block scheme. When there is no need to remove any CO2 or no other process is required. That is the situation below right-hand side. When there is a need for removal of CO2, an amine unit should be placed upstream of the THIOPAQ. In effect, the THIOPAQ itself slips most of the CO2. When to use, or in a different way, when can which technology be used economically? Most gas treatment options could theoretically be used for any quantity of gas containing a certain amount of hydrogen sulfide. But nobody would try and build a traditional Klaus lineup to recover about 5 tons of sulfur per day. Or reversely, nothing beats a scavenger up to a few hundred kilos of sulfur per day. The purple bubble in the middle is our subject today, and I dare say that THIOPAQ Oil and Gas probably has the best papers in most cases when it comes down to cost, safety, stability and environment. Please don't treat the numbers as cast in stone, as project-specific factors can make a difference, but as we have evaluated hundreds of cases together with owners and EPCs, this graph is quite a dependable guide. Here's some numbers divided in lean cases, that is where the off-gas of an amine unit would have an H2S concentration lower than 30%, in which case a regular Klaus burner would be unable to reach a certain temperature. And rich cases, which contain more than 30% H2S in the amine off-gas, which enable the construction of a very simple Klaus unit, which really lowers the level at which a Klaus base lineup can be competitive. For those cases where CO2 removal is not required, THIOPAQ can apply directly to the feed gas, in which cases it can be used up to 80 bar and economically up to 100 tons a day. This little fella is our workhorse. THIO, we call him. And this is a nice start of the introduction of the THIOPAQ O&G process. After the H2S has been absorbed into the THIOPAQ O&G scrubbing liquid, it takes the form of HS- or sulfide, and Theo and his friends can now absorb the sulfide through their body. You can actually see that the body, the tail is on the right. The surface of the body is a membrane. They absorb the sulfide through their body membranes and excrete the elemental sulfur. You can clearly see the yellow sulfur nodules on the outside. We've enhanced it a little bit to make it clearer, but this is really how it works. And this slide shows an animated process scheme of a THIOPAQ. I hope it moves on your screen as well as ours. The process liquid present throughout the system, and it contains over 97% water. The rest is caustic, sulfur and bacteria. And the liquid basically is present everywhere throughout the system. The first stage on the left, the absorption stage, the feed gas enters the bottom of the absorber, and from the top of the absorber the process liquid is sprayed downwards over one or more beds of random packing. The system is operated at a pH level between 8 and 9. The H2S is driven into the solution to become HS- sulfide. The action is really similar to what happens in a conventional caustic scrubber. The sweet gas exits from the top of the absorber and is ready to be used or processed further. The bacteria present in the process liquid are not active at this stage, as there is no oxygen present in the absorption column. They are in fact just passengers coming along for the ride. From a safety point of view, it should be noted that there is no free H2S present in the system after entry to the absorber, making THIOPAQ O&G probably the safest technology around. The absorber itself operates at the pressure of the feed gas. In fact, 3 THIOPAQ O&G units have treated at pressures of up to 80 bar for several years. The next step is the bioreactor section. The bioreactor itself operates at ambient pressure. The sulfide-rich liquid is sent to the bioreactor after the absorption stage. A redox probe indicates the amount of sulfide present in the process liquid. The level is expressed as a millivoltage and in turn controls the amount of air sparked into the bioreactor by an air blower. You can see it happening right on your screen. The amount of air introduced to the bioreactor activates the bacteria, which will now act as a natural catalyst and oxidize the sulfur to sulfur. To help them do so, a small amount of nutrients, which is similar to fertilizer, is added to the system. The third stage on the right is the dewatering stage. Part of the liquid, now heavy with elemental sulfur, is routed to a gravity settler, where the sulfur will sink to the bottom. After further dewatering by a decanter centrifuge, the sulfur emerges from the system as a quite dry cake with about 75% solids. Any liquids are sent back to the process for reuse. As the reaction taking place is not exactly perfect, there is a gradual build-up of sulfate salts, which has to be bled from the system and replenished by fresh caustic and makeup water. We will see later on that this imperfection does not impact the financials at smaller sulfur loads, but rather at higher loads. At really high loads it becomes cost prohibitive, and thus hence the stick over to the cloud-based lineups. As pictures mean more than 1,000 words, here is a THIOPAQ unit treating associated gas in the USA. The load is approximately 1.5 tons of sulfur per day. H2S is removed to less than 2 ppm. Heavier fractions present in the gas are recovered first as NGLs. The methane is sent to the local gas grid. As simple as it may be, this unit actually runs 60% of the time unmanned, evenings and weekends mostly. This is a slightly larger unit with a design capacity of 10 tons per day. This THIOPAQ O&G actually treats off-gas from an amine unit, as the amount of CO2 had to be reduced before the gas can be sold. For maximum flexibility, a total of 5 smaller bioreactors used, visible in the forefront. About HSE exposure, THIOPAQ operations. Recently, a so-called hazard safety study has been executed to compare the impact on safety and other variables, such as maintenance, operations, and health, has been executed by a third-party study. It compares other systems, redox, traditional Claus-Scott lineups, to THIOPAQ, to a total of 5 variables. And you can see that THIOPAQ O&G does perform better, or at least equal, to any of the others on all points. Certainly an interesting outcome, as not all of the reasons to choose a particular technology for a project are purely financial. For instance, the capacity to treat a variation in gas flow or sulfur content can be a very important factor driving customer preference. This is a quite extreme set of fluctuations. Yet the THIOPAQ unit in question keeps H2S below 20 ppm at all times, well below its design value of 200 ppm. In fact, any THIOPAQ O&G unit can treat sulfur loads from as low as 0 up to full design load. A nice, really nice thing to have, you will agree. If we look at cost associated with operating THIOPAQ, the simplicity really shines through here and results in a great transparency of costs. Looking at operational costs, the determining factors are caustic consumption, about 250 kilos per ton of sulfur removed, electricity for pumps, motors, cooling, and to a lesser extent nutrients. The nutrient cost itself amounts to about 30 euros per ton of sulfur. Most measurements are online, leaving an operator to do a visual inspection round once or twice a day, measure alkalinity, and draw a sample into an Imhoff cone. The Imhoff cone is used to assess the amount of sulfur in the system and to inspect sulfur formation. On gas production sites, there is typically no need to hire additional staff for the THIOPAQ O&G operation. Apart from the need to service rotating equipment, there is no need for scheduled maintenance, which creates an uptime of well over 99%. Over 99.9% of the H2S in the feed gas is captured in the process liquid, making THIOPAQ a very effective system at keeping sulfur out of the treated gas and out of any emission to air. Sulfur is recovered mainly as elemental sulfur. A small part is oxidized all the way to sulfate. The picture shows biosulfur produced with a filter press, a very dry, cake-like sulfur. As mentioned earlier, the sulfur is produced as a relatively dry sulfur cake. The slide shows the centrifuge and the cake at the top. When a sulfur melter is included, a Claus quality pure sulfur can be produced, bright yellow. Actually, 3 THIOPAQ O&G units have such a melter installed presently. Our favorite, however, is biosulfur applied in agriculture. The biosulfur produced by the bacteria has a unique hydrophilic character and a very fine particle size that makes it a good ingredient for a range of sulfur-based liquid suspension fungicides and fertilizers. Actually, sulfur produced in the Texas unit we have shown earlier is shipped all the way to the UK and ends up on English farmland. This graph provides a relative OPEX comparison for 5 cases, all acid gas, to make the comparison easier. The numbers are based on a study done recently by leading EPC companies. As THIOPAQ O&G is not as well known as more traditional methods, the numbers for THIOPAQ are probably quite conservative. That is on the high side, even though we want to share these figures with you. And you can clearly see that for lower sulfur loads, the advantage, you can't see that, but actually for lower sulfur loads, the advantage would shift further to THIOPAQ. Reversely, for higher loads, it would shift in favor of a Klaus-based lineup. Some Klaus installations require co-firing of natural gas, which will further push up the OPEX, which is the case in case C. You will notice that the first 2 cases, A and B, are based on lean gases, too lean for a Klaus to burn properly. Sorry, that's A, B, and C, while cases D and E are based on a rich amine off gas, which would allow a Klaus unit to burn easier. This makes a difference in operational cost. The THIOPAQ is the standard, so the bars are always at the same height here. So, especially for refineries and petrochemical installations, the value of the steam produced by a Klaus waste heat boiler may change the operational cost substantially. But as we focus on natural gas and associated gas today, this is a pretty true picture. Now moving over to capital expenditure. How does this simplicity translate into CapEx? Again, the graph provides a relative CapEx comparison for the same 5 cases as the OPEX slide we just studied. Again, lean cases A, B, and C, and rich cases D and E. It's quite clear that the THIOPAQ is lower in CapEx, but it does start to drop off when sulfur loads are higher, especially for the rich cases. Rich cases being, of course, the cases very favorable for traditional Klaus lineups, as enrichment units are not required. We would now like to launch poll number 2, and we would appreciate it very much if you take the time to vote. I can now see it appearing in my on the right-hand side of my screen. Meanwhile, we'll continue the presentation. These basically are the main things we would like you to take away from this presentation. Of course, the order is not anything in particular. For your project, you may value one benefit higher than the other, but this does sum up nicely the advantages of THIOPAQ, particularly the low cost per ton of sulfur removed. And obviously, this is within the segment, the size segment, if you will, we discussed in the presentation. The very simple installation, the ability to accommodate fluctuation in both gas flow and sulfur loads, safety, interesting aspect, especially for offshore operations where it's crucial to operate safely. The limited operator attention is highly valued. At the same time, the H2S removal is very deep, and the sulfur produced can actually be used for re-injection, agriculture. It can be melted for Klaus specifications, or as it's often done, it can also be landfilled. Hopefully, we have made you enthusiastic for THIOPAQ. To make things a little bit easier for you, next time you have a potential project and you want to sort of do an initial quick scan, but then anonymous, without filling out many forms and asking questions, you can do so on our website, www.paqell.com, completely anonymous and instant. If you look at the right-hand side bottom of the screen, there is I will indicate where it is. You can see an orange dot and it says do the quick scan. If you press that button, the next screen appears, and all you have to do is fill in the flow rate for your project in several units. This is millions cups, but there's also cubic meters available. The pressure, the H2S content of the gas stream, the CO2. The sulfur load will appear on the right in tons of S per day, which is handy all by itself. And if you press the button full result and advice, it will actually give you an honest advice based on the cost of a THIOPAQ installation and its particular advantages and disadvantages. This will give you an initial good feel whether you have a potential application for THIOPAQ, and the next step could be sending us the full composition, etc., and we could continue the more traditional way. But this online tool is highly valued. On the same website, we also have a 5-minute version of the process animation spoken in English, so you can recapture most of the things which have been discussed in this presentation. And that really brings us to the Q&A session. We would now like to answer any questions you may have.
Okay, René, thanks for that. Yeah, let's, as you said, let's move on to the Q&A. We've had some good questions coming in. I'll kick off with a couple, René, and obviously you can see some of the questions in the background. So if you sort of make notes on which ones you want to try and address first of all, while I'm asking the first question as well. So, all right. So number one, René, are the bacteria used in the THIOPAQ O&G system genetically modified?
The bacteria actually were dug up from a Dutch field, and they're not modified at all. Of course, a certain evolution has taken place, but they're perfectly natural bacteria, and they occur in any country of the world.
Okay, great stuff. Secondly, how many commercial plants have been built using THIOPAQ technology?
Well, in the oil and gas industry, that number is 10 presently. We have a few under construction, but 10 have gone into actual operation. If you look at the total number of THIOPAQ installations, including those treating biogas, we're approaching the number 200.
Fantastic. And just to remind the audience, we do have a bit of time, so if you still have questions, please put them in now. And just to answer sort of a couple of questions that have come in, yes, the presentation slides or the presentation will be made available within the next few days, and you can also watch it again on demand. Again, it'll be up on our platform in the next couple of days. So next one, René, there's a question come in here talking about, does THIOPAQ remove any types of organic sulfur, e.g. mercaptans, etc.?
Well, that is a very good question. Actually, our initial answer was that we would absorb some of the lighter fractions, but there is actually evidence in some of the units in operation that we see mercaptans going in and not coming out. In other words, the bacteria seem to eat the mercaptans as well, which is an unexpected bonus. And obviously, we've diverted quite some funds to research that in more depth. So the question is, the answer is really yes, probably yes.
Fantastic. Okay, next one. What is the highest feed gas pressure you can accommodate, given the fact that the absorber operates at gas pressure and the bioreactor operates at ambient pressure?
Well, it's not something you would try at a customer site. So actually, the highest pressure we tried in practice is 80 bar. But the answer may well be that the number is substantially higher, but that is something we would have to test. But 80 bar has been done, as that is the pressure of most gas pipeline systems, usually satisfies customer requirements.
Great, thank you. Okay. Another question here. What if my feed gas stream has a sudden increase in H2S? Can THIOPAQ ensure sweet gas H2S will remain on spec?
Yes, the answer is yes, as long as the total amount of sulfur is within design limits. You can imagine that you need a certain size colony to treat a certain amount of sulfur. And as long as that amount is not exceeded, yes, the system can cope with such fluctuations.
Great stuff. Okay. So what we have here is there a limit in terms of amount of gas or sulfur which can be treated with THIOPAQ O&G technology?
There is no technical limit. We could do 3,000 tons a day, theoretically. But I think my explanation on operational cost, if you take a simple calculator and push in a few numbers, you will discover that the economic limit is anything, well, around 100 tons a day would probably be a good mark. So yes, it's possible, but no, it's not economically attractive.
Okay. Okay, we have one here, which is, which kind of sorbent do you use in the first step?
Well, the solvent, really, the process liquid is the same throughout the whole system, and it's about 97% water, a little bit of caustic bacteria, and actually the sulfur. And this bicarbonate solution is present all throughout the system, and it has. It functions as an absorber in the first stage, and it's the environment where the bacteria produce the sulfur in the second stage, the bioreactor stage. I see an interesting question here. What is the upper limit of CO2? I need to scroll up because it was just overtaken by another question. What is the upper limit of CO2 in the gas for direct treating? Well, it's we would like to express that in as a partial pressure CO2, And as a partial pressure of CO2, it's 6 to 8 bar of partial pressure. And that depends on the H2S over CO2 ratio.
Okay. Yeah, we've also got one in here. Sorry, I hope you've finished with that one, René. Another one here is, how would you deal with very hot or very cold climates?
Well, it's actually remarkably similar to the human body. So what you do for starters in the first place is that you take all the variables like gas inlet temperature, the temperature of the environment, etc., the evaporation effect of the air you blow through the bioreactor, and you produce a heat and mass balance. But in some very hot climates, it may be a good thing to keep out the sun, put the unit in the shade, or in colder climates to isolate it against severe low temperatures. What we've done, for instance, in Canada, is that you place the bottom of the unit in a simple building to keep that warm. But really, similar to humans, it can operate anywhere, and we've done so.
Fantastic. Okay. So we have one here. Again, it's is there any influence of higher hydrocarbons or essential oils in biogas treatment on the bacteria?
Well, there is. What we like to avoid is condensable heavier hydrocarbons. It's not a hazard as such, but it causes foaming, which is something you want to avoid. So with just a few simple pre-treatment steps, you avoid condensation of these hydrocarbons, and then you're all right, basically.
Okay. Can the process treat LPG streams?
Yeah, it can be used to use LPG streams. It's the same here. You need to keep condensation away, and as long as that doesn't happen in the gas phase, you're fine.
Okay. So how robust are the bacteria? Have you had any colony die-offs?
Die-offs have never happened in any of the 200 units. What you can see, for instance, if you have some pipe cleaning, you have slugs of valve fluids, for instance, you can see foaming appear, which is an indication that things are not all going well. But let's say before any colony would die off, you would see ineffectiveness and really just less than optimal treat than you're used to. But killing off of a colony is something which has never happened over the past, 25, 30 years. So that's really difficult to do. About the only thing you could try is cook them or add large amounts of biocides, which is obviously never done.
Okay, great. In your process, is there any electric heating elements used?
No, not really. No. We could imagine heating in pre-treatment, but not in the process itself.
Okay, short and sweet. That's good. What is the influence or
removal? That does not include the fact that sometimes pipes are traced and insulated in colder climates, but heating the process itself is not done.
Okay, brilliant. So the next one was I was going on to was what is the influence stroke removal of COS, CS2 or mercaptans?
I think I would prefer to have my colleague Gijs van Heeringen, our Chief Technologist, answer that question.
Well, COS and CS2 are typically removed only very little, so less than 15% of the feed gas composition. So we never guarantee any removal of COS in the first place. And mercaptans is a different matter. The lower mercaptan, so the methyl mercaptan will be removed and it will be converted to DMDS in the bioreactor, and then we have to look at concentration levels, especially compared to the total sulfur, to see how that works out in the treated gas and in the vent gases. The ethyl mercaptan and propyl mercaptan are absorbed much less. It's just basically that the solution is not high enough in pH to really take out the mercaptans like a strong caustic solution would do.
Fantastic, thank you. Yeah, that sort of versions of that question had come in from a couple of people, so thank you for answering that one. So we have one here. Are there any offshore applications in operation?
Not in operation, but especially because of the excellent safety profile and the type of sulfur, which is easy to handle. We do have regular inquiries, but so far they haven't translated into actual units. We have several units on quotation, but we'd like to see that happen in the years to come.
Okay, so there's a question here, or what sulfur recovery percentage are achievable and can be guaranteed?
Well, the actual efficiency is influenced by the pressure in the absorber. And that is quite a steep curve. I think from the top of my head, anything over 5 bar, we typically guarantee pipeline specification around 2 ppm of H2S or less. Lower pressures, the guarantee level is, standard guarantee level is 20-25 ppm, although with, for instance, a twin scrubber, substantially lower numbers can be achieved. So it's pressure driven.
But in terms of say traditional sulfur recovery, as is usually used in the Klaus technology, where Klaus is typically doing 97-98% on its own as a maximum, we typically would say we produce 95% as sulfur, and there is some 5% of the H2S going in, which is produced as sulfate going out with the bleed water.
Thank you. So on to the next one. Which components in common bio or sewage gas have to be removed upstream of unit to avoid problems, foaming, e.g. siloxanes, halogenated components?
Well, that merely depends on the sulfur load of a system. So the ratio between the H2S load and these components. For all of these components, there are certain thresholds which are determined by the total liquid flow, the physical absorption of the components, and the total sulfur load. So yes, typically components like HCN and ammonia do have to be removed upstream, but components like glycol or methanol, we can tolerate quite some of these components in the feed gas, but there is a limit, and that is case depending.
Fantastic, thank you. Yeah, just to remind you, if you do have any more questions, we do have a couple of moments left, and if we don't get around to actually answering any in today's session, I'm sure the guys over at Paqell will be in touch very shortly to follow up with you. So, please do get in touch. Next one then, let's have a look. Do you require any optimum bacteria colony number in the solvent? Following on from this, how do you measure the bacteria colony is good enough for the process?
Actually, the bacteria, they reproduce depending on the amount of feed they get, and the amount of feed is actually the amount of H2S that is fed to the system. Now, of course, we design a system for a certain load of sulfur, and many of times the actual H2S load to the system is somewhat lower, and the bacteria they adapt to the amount of feed they get, and the colony is big enough to handle fluctuations in such way that they can, as René showed in the presentation, handle fluctuations of sulfur load very well. But there is no specific number to give for the number of bacteria per ton of sulfur or so.
Thank you. Let's move on to this one. So why is this technology only limited to medium concentrations, so less than 30%? Is it only cost due to size of equipment, or what are the other limitations that don't allow it to be used for higher concentrations?
That is probably a misunderstanding. THIOPAQ is suitable for any concentration of H2S, starting 0 up to 100%. The 30% level, which was mentioned earlier, is really the level, the concentration where the burner of a Klaus unit starts to function well, making it less, or making it attractive above that number and unattractive under that number. So that is really the answer to this question. THIOPAQ will take any concentration.
Okay, thank you very much for that. Okay, I think we're nearing the end now. I mean, René, what I'd like to do is just come back to yourself, really, and maybe ask for a summary to the audience of sort of, the ideas behind today's webinar and really, the technology moving forward and obviously how they can get in touch as well.
Yes, well, I think the getting in touch is quite easy in Paqell's case. It's www.paqell.com. I had a question myself, really, Simon. Is there any chance you can give us the results of the poll?
Yeah. Okay. So let's publish the poll questions as well. So the first one was talking about, do you recognize the challenge and how have you dealt with it before? So the answers to this were really, it came out as D, yes, we do, and we are still unsure how to proceed with the project. And that was about 58% of the audience for that one. I mean, is that something you expected?
Well, it's obviously something we hope for, because that would give us the opportunity to jump in and help. So that's just about the ideal outcome. I must say it's not quite what I expected, but still very happy with that.
Great. And the second one, so was based on what you have seen. Would you consider THIOPAQ as an alternative solution? So the resounding answer to that one was at 64% for A. Yes, I can see advantages for selected small to medium-sized projects. So yeah, again, René, is that sort of pleasing to hear? Or?
Well, that's obviously wonderful, Simon. Yes, that's really a positive push for us, and all the more reason to continue webinars and speaking at certain selected conferences.
Fantastic, fantastic. Well, it's been a really, really great webinar. So hopefully, again, as I said, I know I've said it before, but if you do have any more questions for René and the team at Paqell, please do get in touch with him or with ourselves directly, and we can pass that on. But really, just to say thank you, René, for what's been a really great presentation, and thanks to Paqell for sponsoring and discussing the topic in this session. Just so everybody knows, the presentation slides and the webinar recording will be available on our platform, on our website, which is www.business-review-webinars.com shortly. We look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned, and follow us on Twitter at BR Webinars for daily updates, and join our LinkedIn group, Business Review Webinars. So once again, thank you very, very much, and we hope you all have a really good day. So thank you, and bye-bye.